Hey, everybody. My name is Alex Merced, and welcome to this presentation, The Who, What, and Why of Data Lakehouse Table Formats. One of my favorite topics to talk about, but first let me introduce myself. So, and also just give you guys a heads up, if you want the slides for this presentation and other presentations I've done at other events, you can scan this QR code. I will put this QR code back up on the screen again at the end of the presentation. But again, if you want to have the slides so that way you can get all the QR codes I'll be sharing out throughout the presentation and all the content, scan that QR code, and you'll have a huge repository of all my different presentations, PDFs, to enjoy. But again, my name is Alex Merced. I'm a senior tech evangelist for Dremio. I spend most of my time talking about table formats, Apache Iceberg, the data lakehouse, which are all topics I'll touch upon during this presentation. But just to kind of introduce you, sort of like what do we do here at Dremio? We are a unified lakehouse platform for self-service analytics. Wow, that's a lot of words. So let's talk about what that means real quick. So, and this will relate to sort of like why this topic of data lakehouse table formats and data lakehouses is so key to my heart, because we are a data lakehouse platform. And generally, we act as that platform on sort of three different tiers. Unified analytics, so we allow you to connect lots of different sources, including your data lakes. So that way you can govern them all from one place and curate your semantic layer from sort of one central location while your data is in lots of different places. We have a query engine that allows you to federate queries that are very high performance across all those sources, and lakehouse management services that allow you to track your Apache Iceberg tables, manage your Iceberg tables, and so forth. So all that is available as part of the Dremio platform. And again, I'm also one of the co-authors of Apache Iceberg, the Definitive Guide. If you want to get a free copy of Apache Iceberg, the Definitive Guide, you can scan this QR code here, which will take you to a page where you can get a free PDF. And again, I'll share all those QR codes again at the end. And again, I'm a senior tech evangelist here at Dremio, was developer advocate, now senior tech evangelist. And basically, I've worked as a developer, I've worked in the data space. I've also do a lot of content creation. So whether it's videos on YouTube, blogs with Dremio, also hosting of a lot of different podcasts, as you see here, Gnarly Dataways, which is like a Dremio broadcast that we do fairly regularly. And then these three podcasts that I kind of do independently to talk about data and talk about basically anything that I find very interesting in this space. So if you enjoy what you hear today, there's definitely more content. But now, with no further ado, let's kind of get into our featured presentation. And to understand what data lakehouse table formats are, you need to understand what a data lakehouse is. And to understand what a data lakehouse is, we need to understand what came before. So before data lakehouses, essentially what we did is we used siloed systems. These would become in the form of databases or data warehouses. What I mean by siloed is that they essentially were a box that had everything. Okay, they would abstract all the aspects of data management, so that way basically you had one box that you could store data in and query it. And those layers that allowed this box to just sort of work would be a storage layer. Like, how do we store the data in that database or data warehouse? A table format, like how do we recognize the different chunks of data in storage as different tables? A catalog, how do we recognize how many different tables there are throughout our storage? Okay, so how do I recognize an individual table? How do I recognize all the tables? And then on top of that, I need some sort of processing layer that's going to parse my SQL queries, take those SQL queries, and create an execution plan, and then actually execute that execution plan. And again, basically, when I would use any database, whether I'm using like a database like Postgres or a data warehouse like a Teradata, all of this stuff sort of would just be sort of baked in, and you didn't have to think about it. And then, databases more on the transactional side would oftentimes have the data more in sort of row-based structures, while data warehouses more on the OLAP or analytical side would have the data in more columnar structures. This was all fine and good. The problem was the data was in the box. So oftentimes, if I liked features from multiple databases or multiple data warehouses, there would have to be like a different copy of the data within each box. So this would result in having to create sort of pipelines to move the data between different places where I need different copies for different systems, then having to worry about keeping those copies in sync, and then the cost of all those copies and using all these different tools. It just became too much. So wouldn't it be nice to be able to take advantage of multiple tools, but only on a single copy of the data? Only if there was like a copy of the data that is sort of open and flexible and accessible like that. Well, there's something called the data lake, where essentially what we have is we still have the storage layer, but in this case, it would typically either be like a Hadoop cluster or object storage like an S3 or ADLS. And that would be it. Basically, we'd store a bunch of data files on there. We had no idea, there was no clear sort of delineation of sort of hey, these files are this table, these are the tables that are available. But we'd still be able to use processing tools like Dremio, like AWS Athena to then run queries on that storage. And that's all fine and good, but typically because of the lack of the layers, table format, catalog, you couldn't really do more sophisticated transactions. Basically, read only, ad hoc analytics. But we wanted to do more because the idea is like we would like to do more of the stuff we do in the data warehouse and in databases and do them directly on this single copy of the data. So we need to introduce those additional layers. And that's where you kind of get into the data lakehouse. Where we take the storage we already had, the processing layer we already had, but now we're going to add in a table format layer. In the case of Apache Iceberg, Apache Hoodie, Delta Lake, the three formats I'm going to talk about during this talk that allow tools, compute tools, to be able to recognize the different tables that are sitting on your data lake. And then a catalog allowing you to track all those individual tables on your data lake so that way you can bundle those tables and make them easily discoverable tool by tool. Okay, and typically here we would think about tools like Nessie. I do separate presentations on Nessie, so I won't touch too much on the catalog layer, but I do have done presentations specifically on that side. Um, but yeah, that's where we are with the data lakehouse. So what we're going to focus on is this piece right here, the table format, because there's three sort of main table formats now that are sort of moving things forward to this data lakehouse type paradigm. Apache Iceberg, Apache Hoodie, and Delta Lake. Okay, we're going to basically in this presentation go through each of them, kind of understand their architecture and sort of how they are built to work. Because understanding how they are structured under the hood will help you understand sort of why some excel in certain areas than others. So, because each of them sort of were designed with a particular context in mind, which helps illustrate sort of the way their features are designed. So the first one is Apache Iceberg. Now, Apache Iceberg was created at Netflix. And essentially what was going on at Netflix is that they were having a lot of trouble using the Hive table format. So before it was all these data lakehouse table formats, there was a data lake table format in the format of Hive. And Hive basically just said, hey, everything in a folder, that's a table. It was really simple because the main purpose of it was really to have a way to recognize the table so that way you could do things like Hive SQL and be able to write SQL statements against your data lake. Okay, because again, Hive's initial sort of purpose was to be able to take SQL and turn it into like MapReduce jobs on your Hadoop cluster. So Apache Iceberg addressed many of the problems that Netflix had, which oftentimes was performance, being flexibility, so being able to sort of evolve your tables, whether it's updating the schema, changing how the table is partitioned, dealing with partitioning. Lots of these features were the things that they were sort of struggling with in sort of just having the sort of general storage of data that they could access really easily. So the way Iceberg works is that instead of saying, hey, this folder is a table, essentially it's all done through the metadata. The metadata acts as a canonical list of the data files that make up the table. And there's a very clear path for which a query engine like a Dremio or AWS Athena will then discover and then scan that table. So in this case, so let's say I'm Dremio or Athena and I'm running a query against an Iceberg table. The initial step is that you go and contact your Iceberg catalog. So the Iceberg catalog will be some sort of service that's keeping a list of all your different tables. And then each reference, so let's say table A, the catalog is going to say, hey, table A, here is the newest metadata.json. So the metadata.json file is sort of the highest level file in the metadata. This is the thing that describes, hey, this is the table. This is the partitioning scheme of the table. This is the schema of the table. Here are the historical snapshots. Basically, all this very high level information that the engine's going to need to kind of understand everything else is going to read going forward. So from that file, I now understand, hey, this is how the table's partitioned. Here's how the tables, this is the current table schema. And then I can understand, hey, this is the snapshot that I want to scan. Now, each snapshot has a file called a manifest list. Okay, and basically that would be the next stop. So basically, once I have that high level information and I've identified the snapshot that I want to scan, I'm going to head over to a manifest list. And a manifest list lives up to its name. It's a list of manifests. Okay, the basic idea is a manifest is a group of files. Okay, so let's say my table is partitioned by date. So probably all the records I have for a particular month are going to be in like one or more data files, and those data files will be tracked in a single manifest. So oftentimes like the manifest match up with the partitions. So I'll have a manifest for this partition, a manifest for this partition, and then the manifest list are going to list all the different manifests that belong to that particular snapshot. So these are the these are the list of files that make up the table for this particular point in time. And the cool thing about the manifest list is that we're rolling up those statistics. So those individual file statistics in the Parquet files are rolled up into, or those individual record level statistics are rolled up into a manifest. So then you have the stats for each file, but then all the stats for each file in the manifest get rolled up into a manifest level statistics that are stored in the manifest list. Now, why this is nice is because now the query engine can go to each manifest, look at the list, those manifest statistics, and say, hey, this manifest, based on the values and the statistics, I don't need to scan that for this query. So I can, instead of having to evaluate each individual data file, I can just skip large chunks of files and say, hey, this chunk of files, not relevant to my query. This chunk of files, not relevant to my query. Typically, you would do this based on partitioning. So you say, hey, the partition values for this manifest list aren't relevant to my query. Out. So then once I've eliminated all the manifests that don't make sense for my query, I then scan the remaining manifests and then I go file by file, look at those stats, and determine which files make sense. So at this point, I've eliminated every file that doesn't make sense for my query. The less files I scan, the quicker my query. Okay, that's the name of the game. The idea is not to throw more processing power at it, because more processing power costs more money. Instead is, how can I do less to execute the same query, so that way I'm faster, but I also end up spending less money because you're not running as much compute. So basically, after I go through that, I have my list of files, and then the query engine will then take those files and then scan those files to execute the query. So basically, the metadata layer acts as a multi-prong uh, pruning layer to prune those files. But because of that, because of this isolation of all these files, this enables things like ACID transactions, all sorts of other features we'll talk about a little bit later. But that's sort of the structure of Apache Iceberg. So typically when you look at an Apache Iceberg table, if I were to do like the simplest Apache Iceberg table, typically you would see two folders in your storage. You'd see a data folder, and this is where you would see all your data files. So you would oftentimes see like Parquet files separated by partitioning. Again, the actual physical way they're laid out doesn't really matter because everything is based on what's inside the metadata, but it still will lay them out in that sort of traditional, hey, here's a folder for each partitioning type way. But it doesn't have to. That's one of the nice things about Iceberg because if you can spread them out, so for example, if you're writing to object storage, you could benefit from actually not putting them in a folder for each partition, but putting them in like just random hashed folders. So that way you don't get throttled when you're making requests to your object storage because you're sending too many requests to the same prefix in S3. So those are some niceties of the way it's structured. But again, you'd have your data in one folder, and then that metadata, that metadata.json file, that manifest list, those individual manifests, all of that would be in the metadata folder. And essentially that sort of would be the file structure when you take a look at an Apache Iceberg table. You'll see that each one's kind of different in the way they structure and lay things out. So again, just to recap, the way Apache Iceberg works from a read point of view, again, the writes are generally always going to work in the opposite, where you work your way from where the read would end and work your way back to the start. So in this case, like a read in Iceberg generally always starts again, as we said before, I check the catalog. The catalog will help me identify the table in its metadata file. I go to the metadata file, get that high-level partitioning schema information, identify my snapshot, go to that snapshot's manifest list, begin pruning manifests, and then once I've pruned all the manifests that aren't relevant to my query, I scan the remaining manifests. And then I can there prune individual files that don't make sense for my query until I end up having a list of files that is the narrowest list of files I need to scan for my query. And that's essentially how Iceberg works. Okay. Then there's Apache Hoodie. Now, Apache Hoodie came out of Uber. And again, when you think about Uber and sort of like Uber challenges, it's dealing with very, very constant real-time data. I mean, you have cars constantly moving people around from point A to point B at any moment in time. So that data needs to come in and be processed very, very quickly. So Apache Hoodie was very designed for handling, basically very low latency streaming. So essentially, to do that, what it is, it took an approach of focusing on timestamps. So basically, the way every commit, every transaction is sort of tracked is based on a timestamp. So that way, no more than one transaction can occupy the same exact timestamp. So then there's an indisputable order of things that allows you to recreate the table at any particular time, even if there's like ongoing transactions, because I can always replay the things that have committed. Okay, so basically what happens here when you take a look at the structure of Apache Hoodie table, again, there's going to be a bunch of partition folders with your files. But now the way data files work in Apache Hoodie is that there's base files and log files. Okay, so the base file is actually the actual like Parquet file that actually has your data. Now there are two types of tables. Like all three formats have a distinction between what's called copy on write, and merge on read. I'll get a little deeper into that later on. But the way Hoodie does it is that you have a base file, that's the actual data file, the original data file. And if you're doing merge on read, which means you don't rewrite the data file every time, then what's going to happen is that it's going to create these log files, and these log files are just the changes to that base file. So I might have a base file, and then I delete a row out of that base file. So then there's going to be a log file that represents that deleted row, and then maybe I add a row, and then there'll be another log file that represents an add of a row to that file. So you end up having all these slices, which is a base file and all of its attached log files. So all of that sits in the data layer. And then you'll have this .hoodie folder, which is where all the metadata lives. And this comes in sort of three categories. Okay. There's a hoodie.properties file, which is where generally all your table level properties are. Like, hey, is this a merge on read or copy on write table? Other table level settings are set there. Okay. Then there's the actual transactions. So the way the transactions work is that when a transaction is first requested, saying, hey, I'm going to do a write, right? What's going to happen is that a file with a timestamp, so this number here represents the timestamp of that transaction, will come in saying requested. So that means that this transaction has been requested. It hasn't finished yet, so the data doesn't reflect what happened, but this transaction is happening. This timestamp has been already claimed. So that means that anything else that's happening has to be at a timestamp before or after that timestamp. Okay, so that way there's again an indisputable order of things. Then as the thing is being done, so as like we're executing the transaction, then that file is renamed to .inflight, representing that, hey, this transaction is currently happening. So just so you're aware, this is happening. And then once it's completed, then it changes to .commit, and that's actually going to have some metadata about the completed transaction that can be used to reconcile things. Okay, so that's kind of like how it manages sort of like ACID transactions. So, which is different than like Apache Iceberg. Apache Iceberg actually technically uses that catalog mechanism, and the catalog mechanism is how you're able to make sure that two people aren't writing at the same time. In this case, it's based on the name of the file and the timestamp number. So I can say, hey, well, someone's already got this timestamp, so my transaction's got to come after. Now, once that happens, there's also a metadata folder. Now, the metadata folder contains a variety of different indexes and metadata tables to help do file pruning. So in the same way that Iceberg kind of put everything inside those three layers of metadata that you could use to identify how the table works, track transactions, and prune files and say, hey, this file I don't need, this file I don't need. Hoodie has that part separate. So again, basically you have the high level, the hoodie.properties, like what does the table look like? You have the transaction side of it, which is those transaction files. And then you have this metadata folder that has the indexes and other metadata for file pruning, for identifying which files you don't need. So similar to how you would do it in Apache Iceberg, based on the partitioning of the table, based on the stats of the individual columns, it'll identify which files don't make sense to scan. So that way it can just skip the scanning of those files. Okay, so just to kind of walk through what a transaction would look like, essentially what would happen is that we would set a timestamp. So if I were to query a hoodie table, I would say, hey, I'm scanning the table, whatever SQL query, based on this timestamp. So now based on that timestamp, it can then go through the timeline of that table, figure out, hey, when is the commit at or before that particular timestamp, and then use that to recreate, hey, which data files am I scanning, and which log files are relevant that I need to apply to those files. Okay. And then basically once we've rebuilt the data, we can then use the file stats and whatnot to skip those data files, and then we can scan the files that required scanning. And that's basically how that would work. Now, yeah, so that's basically how that would work. I'll save the compaction bit for coming up because I'll have a whole conversation about that. Okay, and then last there's Delta Lake. Now Delta Lake has sort of like the simplest setup. It's very easy to understand because it works a lot like Git. Okay, so if you ever use like Git for code, the way Git works is that you would add lines of code and subtract lines of code. So every commit is just a collection of additions and subtractions of lines of code. There's no updates. Okay, if I updated a line of code, it would look like I removed the line and then added it. Okay, so Delta Lake works very similarly, except instead of adding and subtracting lines of code, you're adding and subtracting data files. So essentially the way it works, oops, going backwards, there we go. What's going to happen is that each Delta log file represents a commit, like a git commit. And it's going to say, basically describe the transaction and have a list of files that were either added or removed. Okay, so basically this may be the first commit, so that's just going to be files I added. And then the next one will maybe have added more files. I might deleted a few records, so some files were removed, and so forth and so forth. So in that case, if I were to scan the table, for me to recreate the table, I would just go from the first commit, add and keep adding and subtracting files from the list as I go through, and then I get to whatever commit that I'm scanning to, and then there I've recreated the table. Okay, and then in this case, each Delta log file has metadata about the files that were added. So generally the file pruning happens as you go along. So essentially, hey, I got to this Delta log file and I have this metadata. Based on my query, these files, I should bother adding these files and not or subtracting these files. So basically it's doing that evaluation log file by log file, which is fine. But that could affect performance once you get to like hundreds of log files, right? You have hundreds of these Delta log files, and now every time you want to run a query, you're iterating through these Delta logs to recreate the table. So what you can do is you can create a checkpoint file, and a checkpoint file is basically a summary Parquet file. So I'll say, hey, you know what? I don't plan on going back here too often, like these individual commits. I generally am going to do scans from here going forward. So let me summarize all this data into a checkpoint file. So that way it just has a list of everything up to that point. So that way next time if I want to scan this particular point in time, it'll start here. It'll start with the checkpoint file and then apply each Delta log going after. And that allows you to more quickly rebuild the table. Okay, so that's that. And that's how Delta Lake works. So when you look at a Delta Lake table, there's oftentimes, again, data files. So they'll just be right there at the top level with your partition folders. But then there's going to be a delta underscore log file folder. And that's where you're going to find these files. So you'll find either the log files, which are JSON files, describing each individual commit. And then you'll also see Parquet files, which are those checkpoint files that summarize several commits as one sort of big file. To sort of that way, you have sort of the already curated list of the data files up to that point. And that's how Delta Lake works. Okay, and those are basically the architecture of the three different formats. Okay, and then again, this is how a transaction would look like. So again, what I would do is I would run a query. I would go through each log file to build up that table again. Again, using the statistics that are in those log files, I would then use that to prune files as I go along, and then scan the files that are left. So all three formats have mechanisms, have metadata in places that allow you to say, hey, these files are not relevant. Because that's one of the big points, is to get faster queries by identifying files you don't need. Now, of course, that means you need to manage your data files well. So having data files that are really well sorted, well partitioned, are going to help maximize the value of that data skipping. But we'll have that conversation. Okay, and again, just a little reminder, there should be like an event chat. Let me see if I can find where that is. Okay, and again, so if you have questions as we go along, feel free to put them in there and I'll get to them at the end. But just so you're aware, there should be a session chat somewhere, and I will check that out at the end for any questions. Cool. So now now that we know what the three formats are and their general architecture, let's talk about like the features. All three of them offer ACID transactions, meaning you're going to be able to deal with concurrent reads and writes. Yeah, you have atomicity, consistency, isolation, durability, guarantees as you do inserts, updates, deletes, and upserts. That's a big deal because before that was not a thing you could do in the data lake. Okay, yes, you could always have ACID guarantees on like most databases and data warehouses because again, you're working within the box. Okay, but the idea is how can we get those guarantees outside of the box? And basically, these formats allow that to happen, which is transformational because now you can treat your data lake as your database, which allows you to kind of think strategically about how you approach it. Like, for example, when you have your data like in a box, like a data warehouse, well, then all compute has to go through the data warehouse. Even the smallest transactions are going to have a cost. But when you're working with your data lake house, there are some transactions that you could just use your laptop as the compute. You could pull the data, basically either by spinning up Dremio in a Docker container or using DuckDB or Polars and do that compute directly from your laptop at no cost, um, to do simple things, and then save, the bigger, uh, those multi-node cluster type platforms like a Dremio, Trino, Presto kind of thing for larger jobs. And you can strategically kind of determine sort of what compute should be used sort of for what job. And that's really cool, and you can do it with those guarantees. Okay, and again, that's just sort of the nature of the sort of new paradigm where basically how you process your queries or where you process your queries are separate from the actual physical manifestation of your data. Then there's schema evolution. All three formats enable schema evolution. So you can add columns, remove columns, rename columns, change the data type of columns, reorder the order of the columns. And you can do that without having to rewrite all your data files. Okay, each of them do it a little bit differently, but the idea is that they have a mechanism for being able to track the changing schema. So that way you can apply the new schema to the existing data files without having to rewrite those data files, which saves a lot of money. Again, these are things that we take for granted in databases and data warehouses because they just work. We don't realize what's happening under the hood. Um, sometimes rewriting of files, sometimes not having to rewrite files. Here we can avoid that. We can save ourselves the cost of having to rewrite. Because before these table formats, if you wanted to change the schema of your table, you would pretty much just have to rewrite the table. You would just rewrite the data to new Parquet files. And if you're talking about petabytes of data, that is not a cheap thing to do if you accidentally forgot a column or something like that. Okay. Now, efficient row level update. So this goes back to that conversation I was having before of merge on read and copy on write. So let's talk a little bit about what these two paradigms are. There's copy on write. So generally with copy on write, what happens is that let's say I have a Parquet file with 1,000 records and I update one row. So I'm literally updating just one record out of the 1,000 records in that Parquet file. In a copy on write world, which is the default for all three formats, that's generally the default, it's going to rewrite the entire Parquet file. So I'm going to rewrite all 1,000 records into a new Parquet file so that way I can reflect the update to that one record. Okay? Because again, the assumption with all three of these is that the data files are immutable. Okay, we never update the actual data files because the idea is that the metadata tracks those data files with the data that they have at the time, and you would basically break the guarantees of the consistency guarantees if you started editing the actual files. So the idea is you always write new files. So that's fine. Again, copy on write is good if you don't plan on writing too much, like you're not writing too frequently, because then that's going to be optimal for reads. Because it's going to be much faster for someone to just read a Parquet file with the right data than reconciling things at read time. But what if you're doing streaming? Okay, and you're streaming and data's coming in really fast, and a lot of those things that are being streamed in are updates and deletes. Okay, in that case, copy and write's not going to be fast enough because you're not going to be rewriting entire data files every second. So that's where you would adopt more of like a merge on read approach. So in a merge on read, what you do is you capture the delta, you capture the difference in some sort of other file structure or some other data structure, and then you reconcile it when you read the files. So in this case, for like Iceberg, the way it'll do it is that it creates what's called a delete file. So essentially, like let's say we're doing an update, it would create a delete file saying, hey, ignore that particular row in the old data file. So the other 999 records would still be legit, good to go. And then there would be a new Parquet file with just that one record to be read. Okay. Now that results in a much faster write because writing a Parquet file with one record and a delete file with one line is much faster than rewriting 1,000 rows in a Parquet file. And again, when you imagine this at much larger scales, those differences become much more stark. But that affects read because what happens now during read time, I then have to not only read the old data file, but I have to read the new data file with one record and then reconcile and then make sure I skip that one row. So typically, when you're doing merge on read, you want to do what's called compaction on a regular basis. So that way you're in a sort of parallel process, occasionally reconciling all these files ahead of time. So that way your reads aren't going to be as affected by them because you've rewritten the data files, but just not at the time you did the write, sort of in this other set time. So I might be ingesting data every second, but then I might have like an hourly compaction job that then goes back and reconciles all those files. So that way, when my reads are coming in, they're not reconciling as much. Now, the way Hoodie does it is through those log files I mentioned. So you have the base file, and then if you were to make those merge on read type changes, those would be captured in those log files that are attached to each data file. So then whenever I scan that data file, I would then reconcile it against all the log files that are attached to it. And in Delta, they have a feature called deletion vectors. This is probably like it's the I think it might have just GA'd. It was in preview fairly recently. But they basically have like a separate data structure called a deletion vector that then tracks these sort of deltas and then gets reconciled. Um, yes. Okay. Yeah. I'm still trying to think if I remember if they've GA'd the feature recently or not. But yeah, that's the name of the feature. And the other thing to check is because with Delta Lake, just to keep in mind, like the Delta Lake feature release cadence is a little bit weird because oftentimes what happens is that when a new feature gets released in Delta Lake, first it's sort of only on the Databricks platform because oftentimes the features are built into Databricks' version of Sparks because they have a separate version of Spark that they maintain. So part of what makes that feature work is oftentimes built into their fork of Spark, so it doesn't work with sort of regular Spark. So it becomes sort of a Databricks Delta Lake update or new feature, and then over time, some of those updates will trickle down to open source Spark, so that way you can then use that feature on open source Spark. So there's always a thing you have to be careful for when you're reading the docs to kind of differentiate what features are available where. And I mean that's sort of the reason why, because there's sort of this distinction between sort of Spark on Databricks versus Spark outside of Databricks, which is where a lot of the compute layer of a lot of these features lie. Like a lot of times there's the features like how the table format, like the actual specification, and what the table format can enable a compute tool to do. And then there's what compute tools like Spark, like Dremio, like Trino are able to do with the specification. Like, because again, just because the specification for any of these enables a particular feature, it is on each compute tool to then implement that functionality. So always just sort of keep that in mind. Okay, Z order. Now, Z order, so this gets into the world of data optimization. So one of the nice things that all these tools do is that they try to offer you out of the box solutions for managing your data files. Because while having metadata to be able to fine prune which data files should be part of your scan is great, but it's only as good as the data files you have. Okay. If you have your data files well sorted in a way that leans into your query patterns, then you're much more likely to prune a lot more files than if you didn't. Okay. So clustering matters. Okay. If you partition your data in a way that leans into your query patterns, you could speed up queries. Now, of course, you also want to be careful that you don't over partition either, because that can severely slow your queries. Okay, so like for example, if I partition by like first name, like let's say like I do a partitioning of a table by the first letter of each person's name, but I'm only getting in like 100 people at a time whose first letters are all over the place. What's going to happen is I end up writing a bunch of files with only like one or two people with the first letter A and another one or two people with the first letter M, and that I have too many small files across all my partitions that could result in slower reads. So sometimes sorting before partitioning can be not necessarily a bad idea, because that way, if I'm only getting a trickle of each category, like of each letter, by sorting, I'm still going to have much bigger data files because those data files include more possible values, and then I can always just do a resort. Um, you may be less likely to get a lot of small files. Again, it depends on sort of your ingestion patterns, what you're partitioning by, whatnot. Again, it comes down to just saying, hey, what are the kind of queries hitting? What are the kind of data coming in, and at what rate is that data coming in? Bottom line, like these formats help you solve a lot of things, but they still don't eliminate the actual engineering and data engineering. Um, so, but bottom line is that all three of these formats have a way to do Z order sorts. So they all have clustering tools that allow you to sort your data when you rewrite it. Okay, because periodically you are going to want to rewrite your data files either through because of compaction, take small data files, turn them into big data files, or take lots of small files into fewer bigger files. But when you do that, you might want to sort the data. Okay, all of them have the ability to just sort on a single column, but now they all also have the ability to do Z order sorting, which allows you to sort not just on multiple columns, but in a way that's evenly weighted across multiple columns. So as an example here, imagine we have two fields, X and Y. If I do a Z order sort, what's going to happen is that every record is going to fall into one of 4 buckets. So in this case, let's say a value of X between 0 and 50, Y through 0 and 50. So what I would do is I would sort all the records into these 4 buckets, and then these would have unique data files written versus these data files. Okay, or basically they would be sorted in the files based on which bucket they kind of fall into. So this means this would be useful if my queries typically filter based on X and Y. So if I'm looking between, hey, I'm looking for an X of 75 and a Y of 75, then I know that the only data files that matter are the data files in this bucket here. So these 3 buckets of data files can be immediately pruned from my query. So again, if you run queries like that, and those are your typical query patterns, Z-order sorting can be really beneficial, and all of these have tools built in to help you just execute that. So that's always a nice thing. Also, lakehouse versioning. Versioning's a big deal nowadays because one, data quality is a big deal because especially when we're building a lot more AI and ML, and that's sort of like the big sort of hot focus of the world these days. Um, you need a way to kind of manage quality, and the way you can do that is through versioning your data by saying, okay, hey, let me create like an isolated branch in which I can make changes to my data and then merge those changes back in. And there's sort of 3 ways you can do this. You can either do file versioning. This would be using a tool called LakeFS, where you would basically, you're not isolating changes to the table, you're isolating changes to the file system. And then you can then merge those changes back in. There's table versioning. This happens in the Iceberg metadata. So what you would do is that you would actually create a branch of commits to that individual table, and then you can basically make one of those commits the head after the fact. So essentially merge it. And then there's catalog level versioning, where you capture commits at a catalog level. So you're not capturing one table, but the whole catalog of tables. And then what you can do is that you can do a branch, make changes to all your tables, and then merge those in when you like. So it just depends on sort of like what kind of transactions you're doing. If you're looking at multi-table transactions, you might prefer catalog versioning. If we're talking about just changes to one single table, well, then table versioning might work. So different formats have different types of versioning accessible to them. Like Iceberg has all 3. Okay, table versioning is built right into Iceberg, like it's built into the spec. Catalog versioning is executed through a open source tool called Merced that actually basically has commits, Git-like commits, but at the catalog level. So that way you have the table level commits built into the Iceberg spec, but then you'd also have the catalog commits built into the Merced catalog. Now Apache Hoodie and Delta, they would basically the only option would be LakeFS and file level versioning in order to execute sort of that same level of isolation and experimentation. Neither of them have table level versioning outside of like that. Outside of being do time travel, you're not able to like do branches and tagging and merging directly in a Delta Lake or Hoodie. And then neither of them currently work with Nessie, although it's not. It's basically if you understand Nessie's architecture, it's totally possible that Nessie can work with Delta Lake and Hoodie in the future, because it's not capturing necessarily the specific metadata of the table. It's just capturing a reference to the location of the table. So you're just versioning that reference. So theoretically, in the future, it can. I mean, there was an effort to have Delta Lake support in Nessie that required some pull requests to Delta Lake that never got pulled in. But in the future, it's still possible. So we'll see. Then partitioning. Partitioning is another sort of important story because partitioning is one way to really accelerate the performance of your queries. Okay, but the thing is that back in the days of Hive, there were problems. Okay, and basically what I meant is that partitioning wasn't necessarily as easy as it could be, and that leads to more mistakes. And mistakes meaning full table scans, really expensive, long-winded queries. So Iceberg has a feature called partition evolution that allows you to update how your table is partitioned. It's the only format that can do that. So you don't have to rewrite your whole table to change how your table is partitioned. But it also has a feature called hidden partitioning that makes life easier for the data engineer because I can then express my partitioning based on a transformed value of a column without the need to create an additional partitioning column. Because in the past, if I wanted to take like a timestamp and say, hey, I want to partition this by month, I would have to create a separate month column. And then every time I ingested data, I would have to make sure I create that month column. So that would be physically another column that would have to be stored in my data, and that'd be another sort of additional logic that would have to be part of my ETL jobs. And then on top of that, the data analyst would have to know to query not just on the timestamp, but also based on that month column in order to take advantage of that partitioning. So it required a little extra work on the engineer and the analyst. With hidden partitioning, essentially the engineer can just say, "Hey, I want this partition it based on the timestamp column by month." No additional column needs to be made. The iceberg metadata kind of handles the work from there. So you have smaller data files, and it's a lot easier to execute. You don't have to change your ETL job. It's just you just express it when you create the table. And then from the data analyst point of view, they can just query based on the timestamp, and they don't need to know anything about how the table is partitioned. The table will naturally benefit from that partitioning. Delta Lake does this from has a similar feature called generated columns. The big difference with generated columns is that you are still generating that additional column, so you are physically storing that extra column in your Parquet files. But it um, basically Spark, because again, it's basically the actual like functioning of this feature is built into Spark. Spark will then recognize that column relationship and then be able to generate the additional column automatically for you, so you don't have to write the additional logic in your ETL work. And then when an analyst queries it, it'll know the relationship between the two columns, and the analyst still won't have to write the additional predicate in their queries. So you still kind of get to the same place. You just still have the additional storage. Uh, Hoodie doesn't have a way to sort of update partitioning, but essentially what it does, it leans heavily on that its indexes and metadata table to basically make that unnecessary. The idea is basically, since they have all these different indexes built into into how the format tracks its data, it can oftentimes quickly identify what it needs to scan and not. That these considerations become less so. At least that's the argument. Then basically now we're getting to the end of the presentation. The last thing to talk about is format interop. That's a big topic because now there's multiple formats. People like different formats for different reasons. Like, oftentimes if you're doing AI ML work and you're using Databricks, you're probably going to want to use Delta Lake because everything's kind of built around Delta Lake there. But if you're doing streaming, well, Hoodie's really built to handle sort of like that really low latency streaming and a lot of those streaming considerations. And if you want to connect to a much larger ecosystem of tools, Apache Iceberg is going to have one of the largest ecosystems and most flexible sort of ecosystems around. Oftentimes being a really good format to sort of be your default home format. So a lot of times, like people are thinking, like, how can I make all these formats work together? There's a couple different projects going on. One way you can do this is use a Lakehouse engine that supports multiple formats. Okay, this could be something like a Dremio that supports Delta Lake and Apache Iceberg. OneHouse created a project called OneTable that's recently become an Apache project called Xtable. And basically, what this does allows you to transfer between the different formats systematically, and then it's built in a way that in the future could accommodate future formats that get created. So I think they are building the ability to do Paimon, which is a fourth format that's streaming related, Flink related, that's come out, but still fairly new in the space. Or using Delta Lake's Uniformat. So Delta Lake's Uniformat, essentially what it does is that it generally works with like Unity catalog. So you kind of have to use Unity catalog, which is a Databricks feature, to truly take advantage of this. But essentially what it does, it will write, as you write your Delta Lake tables, it will then write a Hoodie or Iceberg metadata and then track that metadata within Unity catalog. So that way you can access that version of the metadata from the Unity catalog. And basically, eventually it's supposed to go both ways where you can, but right now it's mainly Delta Lake to other formats. So basically your Delta Lake table would be your main data, and then you just have these mirrors of that with a couple catches. Like one, like if you were to write like a lot of transactions to that Delta Lake table really quickly, you would have a Delta log for each transaction, but you might not have a Hoodie or Iceberg snapshot for each transaction. It might batch those transactions because it's writing the metadata asynchronously. So in order to kind of keep up, it'll batch transactions. So you're not going to get the same exact consistency per se, because there might also be a lag between when the mirror version updates versus the original version. So these are just some things to keep in track when you're using these kind of tools. But yeah, that hopefully gives you a better idea of sort of like the world of the data lakehouse table format and the data lakehouse and how these formats are architected and the features that they have. But again, if you want to learn, I'm one of the co-authors of Apache Iceberg, the definitive guide. If you want a free copy, just scan this QR code and you'll get a free copy and you can read all about it. A lot more content there um, about all sorts of cool stuff. Also, if you want to get hands on and actually try this out without having to set up some huge cloud infrastructure, if you scan the QR code here on the left, it'll walk you through an exercise where you'll literally spin up a Nessie catalog, Minio for your data lake storage, and a Dremio for a query engine, all on your laptop. And you can actually do some transactions, create some iceberg tables, actually see those iceberg tables in your object storage, and have a better understanding of just sort of how this all works, and by through some hands-on exercises. And then on top of it, here are three exercises that kind of take that to a next level where you actually go end to end. So these three exercises here, you'll start with a database, so Postgres, SQL Server, Mongo. You'll have some seed data in that database. You'll ingest it to an iceberg table using Dremio, and then feed an Apache superset dashboard at the end. So you'll literally walk you through the end-to-end sort of data engineering workflow uh, in this case with Apache Iceberg against any of these databases. So these are also fun exercises. Again, these can all be done straight from your laptop, so they require no cloud infrastructure, no opening accounts anywhere. You can just spin up a few Docker containers and do the whole exercise end to end. All of these can also, these and more, I just actually published two more, one for Elasticsearch and one for MySQL. And I should have Apache Druid one, hopefully by the end of the week. And you can find all of those at dremio.com/blog. And again, subscribe to my podcast and follow me on LinkedIn. Okay, so you can find all my information here. These are all, you can find all of these on iTunes and iTunes, Spotify, whatnot. And here we talk about all sorts of data type concepts all day, every day, because that's what I do. But with that, I think that's pretty much the end of the presentation. So now what I'll do is I'll take a look for the chat, see if there's any questions. Let's see, I'll figure out how that. Oh, there, I think I found it. Okay. I see no questions. So I'll give a moment for anyone who wants to ask a question. But I just want to say thank you so much for being here at this presentation. This is always a lot of fun to talk about these topics, these concepts, and I appreciate you all joining me in doing that. So you guys all have a great day, and again, enjoy the rest of the Gen AI tools and infra and open source demo day. And I'll see you all around. And thank you so much. Thank you for all the kind words. I'll see y'all on LinkedIn and other places.